Thank you for joining today's webinar on Introduction to IoT Security. Today's webinar is hosted by Microsoft, a signatory of the Cybersecurity Tech Accord. Last year, the Tech Accord announced a new partnership with a global forum on cyber expertise to strengthen cyber capacity building through the exchange of best practices. To further our commitment under that umbrella, we launched a series of webinars to help increase the understanding of key cybersecurity topics, such as the one you will hear today. Today's webinar is presented by Rob Spiger, Principal Security Strategist at Microsoft. Rob is a Principal Security Strategist on a digital diplomacy team inside the Microsoft Customer Security and Trust organization. Rob leads the team policy work on the Internet of Things and artificial intelligence security. Rob is an industry security expert with in-depth understanding of trusted computing technology and standards development. We'll welcome you to share your questions in the chat box located to the right at the end of your screen, as there will be time at the end of the presentation to answer questions. And now I'd like to welcome Rob.
Hi there, thank you very much for the opportunity to present to you today. What I want to talk about is IoT security, and this is obviously a really big space, so I'm going to try to focus on the slides that I work on. First, I want to set some context for IoT, and then I want to compare kind of what we've done for traditional PC security around trusted computing with what we can do for IoT, and look at some alternative options that are more appropriate for IoT in some circumstances. And then I want to get into kind of how we can establish trust in IoT devices by talking about roots of trust. And finally, I will end with some recommendations for the industry to try to improve IoT security as it's brought to the market today. So to start off with and provide some context, what is the Internet of Things? Well, there's no specific agreed definition. And I think if you try to pin someone down, they will be a little hesitant to provide a precise definition. But overall, it's something that connects to the internet or a network. And examples are sensors that collect data, things that control the physical world. These could be safety related, or they could just be very minor, like turning on a light switch. Generally, these are embedded systems that have a dedicated function, but they could also be more complicated devices as well. And then traditional industries are taking products that hadn't been on the internet before and just kind of connecting them to the internet, maybe to help monitor those devices for maintenance, or be able to send telemetry back about how much they're used or things like that. So all of these connect devices to the internet and generally, provide some interaction with a cloud service or application that a user uses to help control the devices or benefit from them in some way. There is a significant potential for IoT to really make the world an awesome place. I think there's also some risks associated with that are brought up by the security risk for IoT devices. IoT could revolutionize manufacturing. It could collect real-time data in large volumes. That is excellent things to try to feed into machine learning models and predictive analytics, and be able to have better business insights. You could also do predictive maintenance. For example, you may put sensors in elevators and be able to send out a technician before someone gets stuck in it. The continuous loop of data from a device and analytics on the back end really have a potential to improve people's lives. Medical devices is another example, and there are just so many more. That's why there's so much interest in IoT. But with this benefit potential comes the danger that there will be so many IoT devices online. They potentially will have vulnerabilities that can be exploited, and they might be taken over and used for malicious purposes. There's going to be so many of them that people won't go and manage their IoT devices. No one wants to touch every light bulb in their house for a software update. And so, there really needs to be a consideration of how these things could be automated. And finally, with a laptop or a phone, if it's not working like someone expects, that they'll probably notice. If it's an IoT device, that there may be no good way to check if the device is doing what it's supposed to be doing. It might be hard to identify the device or know you're even communicating with it. People may just not pay attention because they'll potentially have so many IoT devices in their lives over time that a malfunctioning device might go for years without being noticed. And there's not just the risk of a device being compromised and the data that's on that device. IoT devices can be stepping stones for other attacks. If they have some ability to control the real world, they might, unlock your front door, for example, or do other things that impact safety. And if we're going to use data from IoT devices to make important decisions, if that data is corrupted because the devices are infected, we're going to make bad decisions. So the question is, what can we do about that? I think part of that solution involves understanding a little bit better about IoT devices compared to traditional devices. There is this kind of relentless push to make IoT devices low cost due to the large number of devices that might be deployed and the different application areas where they could be used. They also aren't necessarily something you're going to want to plug into a power outlet. So they're designed to use very minimal power. Maybe they could be run on batteries for several years. They might be embedded in the materials where you can't go and change the power source. You can't change the batteries on it. They might not have a display or any output. These are all things that are really different from a traditional PC. And people just aren't going to supervise them as carefully as they might larger devices that they interact with on a daily basis. The hardware manufacturers for IoT devices have real extreme competitive pressures. They are really trying to provide the functionality needed for different scenarios, but they're making huge trade-offs around cost and features. And I think in a lot of the earlier architectures we've seen, security took a back seat to could we just build something that's able to be online, is able to run on the battery for a long time, and maybe have minimal processing power, but can still do a specific piece of functionality. The IoT device life cycles are a lot faster than PCs. I've got some history in the PC industry, and it takes a while for new products to come to market. I think IoT devices really have faster iterations. And the security techniques that are used on PCs or servers today really aren't cost effective for some classes of IoT devices that are probably going to be the most widely deployed. And so there really is a need to search for new security technologies. And today I want to talk about some of those and kind of focus on the goals of what we're able to do in the PC space. Just to kind of set the landscape and the rest of the context, I want to talk about the different roles in securing an IoT device. I generally think of it as there's an IoT hardware manufacturer that's going to make an IoT platform that is generic and doesn't have any specific functionality. And then a IoT solution developer is going to come and add functionality to that IoT platform by writing software that does a specific function or integrates with another device, maybe a washing machine or something like that. And they will produce, the specific functionality in the end product that someone's going to actually purchase and use. And then finally, in the rest of the life cycle, there is someone that deploys that solution. And hopefully there is someone that manages and maintains the solution, that understands if there's a software update that needs to happen for that device and is able to make sure that gets installed properly so the device can be protected going forward. So if you look at the first two participants in this process, the IoT device platforms are really generic, and they generally have some sort of network connection. Some may have a display, some don't. They may have some electrical signal that can be used as an output to control whether something else is on or off. And the IoT platform manufacturer really has to provide some specific code for the device that helps initialize its devices and capabilities that it provides, and also provide a way to get code onto the device, to be able to write software for it, to debug that software during the testing phase. And there's really this heavy dependency on the platform manufacturer to provide, really a way for a developer to integrate with it and make it into a finished product that has a specific functionality. The maker or the IoT solution developer will take that IoT platform and customize it for the specific purpose. When they go to actually mass produce these things, they generally have a choice of, they could ship their solution using the generic IoT platform that they started with. It's often provided from hardware manufacturers as a reference platform for development and testing, but those are also low cost. So, you could ship a product with those, or you could go back, and if you're going to do enough volume, it may make sense to do a dedicated hardware run of that specific device embedded in a specific way with just your functionality. If you do that, you might take off extra devices or things that aren't needed that are part of the reference design that the IoT platform manufacturers produce. And then finally, when those things are deployed, there is a lot of steps to get those provisioned and configured, to figure out who owns the device and configure it and connect it to a cloud service to manage it. I'm not going to focus so much on that today. And another piece is really maintenance. Software solutions have vulnerabilities. Maybe when the device is initially manufactured, the process used to develop that software uses all of the industry best practices to try to produce as secure a software as possible. But new attacks are always being developed all the time. And so what was considered secure yesterday generally won't be secure tomorrow. And there's this general need in the industry to keep doing updates to fix vulnerabilities. Next, I want to talk about kind of the security piece of IoT devices by looking at the boot process and how does security work during boot. I'm going to first look at a PC platform, and I want to look at this from the lens of how can recovery happen. Let's make the assumption that software will get compromised on devices, and look at how the recovery can occur and what we could do to improve that process. So for a typical PC or server, there's kind of three phases to the boot process. There's some stuff that's really in the realm of the platform manufacturer, where only they know how to initialize their platform and get it started. They've got different devices or components on it that are needed to really be able to have other code that's written by anyone else run on it in a way that's useful. Generally, this has a secure boot process where if the wrong software has been installed, it'll stop and go through some sort of remediation process for it. But a lot of times, this early code is really critical for the platform manufacturer to maintain control over and make sure nothing happens that's updated into a bad configuration or with malicious software. So generally, the very early boot process starts a root of trust for update that's going to verify an update before it can be installed and persisted for the early boot code. And it may also start a chain of measurement that's going to help show later on to someone else what software was loaded during the boot process. On PCs, there's kind of a pre-boot environment that's fairly well standardized by UEFI. That's the Unified Extensible Firmware Interface. It's an industry standard that's been worked on for quite a long time. That has some capabilities to make sure that components loaded in this environment are signed properly according to a policy. And then finally, that's really used as a stepping stone to launch an OS that has applications in it. Generally, an OS does enforcement of its own security policy, maybe in conjunction with an AV product, or maybe just straight by itself. If you look at this and break it into two different pieces that are really important today, the early steps 1 and 2 are really layers that help support recovery of the OS if it's been compromised. The OS is, the usual runtime environment where there is a lot going on and a lot of different applications. There's a large code base usually for the OS. If these are infected, someone generally, notices their system's misbehaving, their AV software may have a warning, something else on their network may flag to them that, hey, the system needs attention. And then the IT administrator or the owner of the platform can use really the firmware that's in the early boot phases to be able to reinstall a new OS and put it into a trusted state again and use it. That means there's a lot of security that goes into making sure that the firmware stays secure. I think that's improved lately in the industry, which has been great. In contrast, the IoT boot process doesn't have a sophisticated interaction during the boot process. There is usually some initial boot code that's from the manufacturer and manufacturer specific. Ideally, this also has some roots of trust that verify updates before they're able to be installed, and also start some way to measure and report later on what software was loaded. What's really good to add into an IoT boot process to improve security is a step to check for recovery or update actions that need to happen. Really, early boot is the safest time for an IoT platform if the update of that early boot is carefully controlled. So having a step during the boot process that checks if an update needs to be installed, verifies it before it can be installed, and then if there isn't a need to do an update, locks all of that early boot code and its persistent storage, that can be a safe way to transition to a larger set of code that provides device-specific functionality. So having step 2 really provide a root of trust for update and prevent updates from occurring to that early code later on is critical. The third level could be an OS, or it could be application-specific code on an IoT device. Usually they're very slimmed down, so it is just specific functionality for a specific purpose. If you think about recovery of these components, really what it makes sense to do is break up that early code into something that stays secure and consider the application-specific functionality or even the OS as something that could potentially be compromised. Somebody can't just come and repair this as interactively as they might with a PC. You need to have that early boot code be able to automate that recovery process. And somehow it needs to know that recovery should happen, or that the software it's running is out of date and needs to be patched. The Trusted Computing Group is working on how to kind of refine these concepts. For the example of IoT, they would categorize steps 1 and 2 as a resilience engine. And then step 3 is the resilience target, the thing for which resilience might need to have activities happen to repair it. So kind of looking at how the Trusted Computing Group, which is a standards organization, might look at this, there's a resilience target, which is really mutable code and configuration information, the functionality of the OS. Ideally, it's where you put most of your code. And then you could have a smaller base called the resilience engine that's able to do recovery of that resilience target. And by servicing, that means it could update it, it could reconfigure it, it can make changes to put it back into a working state. And finally, that needs to take instructions from something that lets it know that things need to happen. The Trusted Computing Group calls this, in the current work they're doing on this, the resilience authority. Ideally, that's in the cloud, so it's separate from the actual device. It has some form of communication with the device manufacturer, who's ideally monitoring whether there's a vulnerability or some incident out there for security with those devices, and can help the solutions operators know that recovery actions need to get sent down as instructions to the device. Now, the challenge is, if we have this early process in boot, how can we get it to go into a recovery phase, a recovery process? So looking back here at this last slide, one of the things that we've got in the middle of step 2 is it sets up a way to regain control in the future. So, before you transition to the OS or application code, somehow you want to be able to make sure this recovery process is able to be activated. So looking a little bit more at what the Trusted Computer Group is doing, they are working on some building blocks to help provide a way to do resilience. They're working on kind of how to define a secure execution environment, which is that safe place to stand in step 2 to do recovery actions in the recovery engine. And they're looking at how could they define storage protection latches to write lock or even read lock the early boot code. So once you transition to a less trusted OS or functionality in an IoT device, it won't have an ability to be able to change that persistent stored image for the early boot code or the resilience engine. And then finally, it's looking at ways to regain control. If you've got the assumption that the resilience target's been compromised, malware in that environment might just try to keep the platform running forever, so a recovery process never happens. One thing that is conventional in the industry is a watchdog timer that you set, and if something doesn't complete or the time elapses and it isn't stopped, then it will recycle the platform so recovery can happen. That's helpful for robustness, but it doesn't help if malware gains control and specifically turns off that watchdog timer. The other type of timer that Trusted Computing Group is working on as well is a latchable timer, where once you set it, it doesn't reset until the platform power cycles. Now, you could make this happen so, maybe every night the device reboots and it goes back into that recovery process in step 2 and can repair things. But this can be a little bit problematic for implementations because it's going to unconditionally power cycle the platform on some regular interval to be able to check for recovery actions and perform them. The kind of next step up from that the TCG Cyber Resilient Technologies Workgroup is thinking about is an authenticated watchdog timer, where if you can get something else to sign a ticket or to confirm that the device is healthy or updates don't need to happen, then that timer doesn't trigger and the platform doesn't get reset and the recovery process doesn't need to happen. On the other hand, if the authority that's interacting with this device knows that there are updates from the manufacturer and that the code the platform has currently got on it is out of date and has some vulnerability, it could just not sign the ticket to be able to extend how long the device can keep running. So either malware gains control and stops, it tries to stop the timer but can't, so the platform gets restarted. Or if malware does gain control, but the information about how the platform booted, it's able to provide to an authority to try to get a ticket to keep the platform running longer, is out of date, the authority won't sign the ticket, and then the end result will be the authenticated watchdog timer isn't deferred or stopped, and the platform is restarted so that earlier step 2 can go through a recovery or reconfiguration process and fix things. And then finally, the last thing the Trusted Computing Group Cyber Resilient Technologies Workgroup is looking at is a wake-up timer. You might have malware for an IoT device that gains control of that OS or functionality environment and then just tries to put the platform to sleep. Most IoT platforms have some provision to go to sleep and save on power usage. You don't want malware to just be able to turn off the platform permanently. And so, IoT devices need to have some security capability where either a timer wakes up and resets the platform, even if it's been put into a low power state, or there is just a maximum limit on how long an IoT device can be in a lower power state before it's started back up and restarted to be able to go through a recovery process. All of these are really trying to address the fact that there's not a human interacting with most of these devices and caring for and feeding it. Instead, these security techniques are a way to try to automate both the re-entry into a process that's able to do recovery and protection of the storage for that early boot code and the recovery engine. So, even if there is a compromise in the larger code base area, that early boot code that does recovery is still able to be functional. Then, a lot of this depended on how do we know that an authority can assess whether a device is running the right software or up-to-date software. To be able to really do that effectively, you need to have an identity for the device, and you need to be able to have some way to prove what software it's running. Traditional techniques have used roots of trust to do that. A root of trust is something that you inherently have to trust that it's going to work correctly because its misbehavior cannot be detected. And so, what you want to do is build roots of trust that help provide a device identity and information about what software is running into your platform design in a way that they won't be tampered with or it can't be compromised. So the traditional PC model to do a root of trust has been kind of developed as a trusted platform module, which is a worldwide standard for trusted computing. Basically, the TPM is a separate hardware component that has some sort of isolation boundary that's completely separate from the software environment. And it's able to receive commands and return responses. And it has support to do cryptographic things like create keys and protect them. It's able to store keys in a way that they can't be tampered with. It has policies for how those keys can be used that you could specify when you create the key. And those can be protected by dictionary attack logic, so somebody can't just guess the authorization to use a key. They also have a provision to store integrity measurements and be able to report on what those measurements are. The integrity measurements can record the software that was loaded during the boot process and its configuration. And then the reporting piece allows the TPM to be able to show those measurements in a way that a third party can trust by looking at a report or a quote. And then finally, TPMs have a provision for identity. I mean, if you're going to rely on a trusted platform module to provide some security functionality, you want to be able to actually know that you're interacting with the TPM when commands go to it and you get responses back. To help support that establishment of trust and a trusted platform module implementation, it has things called endorsement keys that are basically things that are identity for the TPM. They're cryptographic keys that can never come off of the TPM based on how it's designed. They stay internal to it. And the manufacturer of the TPM can sign an endorsement key certificate to say, if you see this endorsement key in a TPM you're interacting with or anywhere in the world, because I've signed this endorsement key certificate, you can be assured that it's a TPM my company manufactured. And it's going to have the right security properties according to the standard for how TPMs are supposed to be built and implemented. And then finally, there's some other information about a TPM that it can do, or capabilities like storing information in a protected way, or allowing the owner to reset things like the dictionary attack logic. If you take this and put this in the context of a PC platform, or even an IoT device, this is really helpful for security scenarios. The software environment that's on the device can send commands to the trusted platform module to do things like create keys or record measurements. Because the TPM has this isolation boundary around it, there's no other way to interact with the data that's in the TPM or the keys or the measurements other than through defined commands that are part of the TPM standard. There's ways to add more measurements, but there aren't ways to erase the measurements during a given boot cycle. There are ways to create keys and specify that they remain inside the TPM. It can't be exported. But if you specify you want a key that is not exportable from the TPM standard guarantees that key will always reside in the TPM. This is a great way to do identity for a platform. The identity of the TPM can be thought of as the identity of a platform, and it can be used as a long-lived device identifier. The types of security scenarios that happen in traditional PC platforms can happen just by sending commands to the TPM in the right sequence to do security and privacy goals. If you look at kind of an example of how this would work, there's a TPM command to create a key, and you could create a device identity key, for example. And you can specify that to use the key, the TPM has to have certain measurements of the software state that was used to boot the device, or you might have to provide a PIN value to use it. And dictionary attack logic that's in the hardware and that isolated boundary can help prevent guessing that PIN value by locking out too many guess attempts at a time. So this is kind of an illustration of activities software might do. If it wants to create a device identity and have the owner of the device, confirm that's their device, they could do it in a way where they can make a key in the TPM. They could prove that it's in the TPM by using the TPM's endorsement key, and the endorsement key certificate can give them comfort that the TPM was really from a TPM manufacturer. And they can have a long-lived device identity created and protected. If you did have malware that took over the software environment on the device, it wouldn't be able to export the identity key. So if you do have a compromise of the software environment, you can still reestablish trust and still rely on the device identity as being unique for that device, because it'll never be exported from the TPM and somewhere else away from that device. If you want to have your device authenticate with a cloud service, using a key that's bound to the TPM to do that is perfect, because after your device gets compromised, they can still have the same device identity. You still know the malware might have been able to use it for a limited period of time, but once you've removed the malware in the software environment, you can still trust the device identity. You wouldn't have to re-provision it. The other thing TPMs are good for is being able to have a log of integrity information about how the platform was booted. This starts by some initial component that's your root of trust, that you really have to trust works correctly to do this measurement sequence. Some initial component loads component A and measures it. That's by taking a cryptographic hash of it. And then it sends that as a command to the TPM in that isolated environment to say, I know you just turned on, everything's been initialized. Here's the first measurement of component A, which is the first software that's loaded on the system after we're starting this measurement chain. And then component A will get control after its measurement has been recorded in the TPM. It can't send a command to erase that measurement in the TPM. What component A is and what its measurement was has already been put into the isolated environment in the TPM, and it can't be erased. Component A can then load component B, take its measurement by hashing it, and then send another command to the TPM to say, here's the second piece of software that was loaded. Add this to the integrity measurement storage that you're maintaining. And then component B does the same thing with component C. And you can have this unbroken chain of measurements of the software and configuration that was loaded in the boot process, placed in the TPM. It can't just be reset unless the platform is reset and boot starts again. Having it isolated in that isolation boundary of the TPM provides that extra security. And then finally, the TPM is able to report on what its current measurements are for integrity. So the software goes through this process of extending the measurement or the hash of components A, B, and C, and so on up through the boot process. And finally, software can ask the TPM for a quote of the current measurements. The TPM takes the current measurements and it signs them with a key. That key is usually associated with the identity of the device. And so the quote that's generated can show evidence of the device state that can be sent to a third party so they can know what software booted on that device and what its current state really is. This is something that's impossible for malware to tamper with, because malware may get loaded, in component A, B, or C, but the fact that malware is in there is reflected in the measurement of that component, and that's going to show up in this eventual integrity report. The integrity report can tell somebody that's like a resilience authority or some cloud management of an IoT device, whether the software that's on a PC or an IoT device is is the current version or older version. So kind of to recap, the key benefits you can get from a trusted platform module is it's a hardware root of trust that's not possible to do with software alone. For software, really whatever runs first owns the platform. Having this separate isolated boundary that can hold measurements and create keys and manage them really gives a stronger way to do security that's just not possible with software by itself. The TPM lets you create and protect cryptographic keys that can be used for authentication or the device identity. And the close integration by starting that measurement chain by the platform and recording those measurements in the TPM during boot provide transparency about the whole boot process. And you can do device health scenarios by reporting on the platform integrity measurements and sending those to another server or device. The challenge with TPM is it's great for PCs where an extra 50 cents or $1 is okay to add to the cost of a platform to get all these security benefits. But for some IoT applications, the 50 cents or $1 for TPM may be as expensive as the platform itself. So if your IoT solution can support a TPM in terms of the cost and the need it has for security, that's great. Use the TPM. If it can't, there's another alternative that I want to talk about next. We have these key goals of knowing the device identity as well as what software is running, but we maybe don't want to spend that separate expense of having an isolated execution environment for the trusted platform module. So the Trusted Computing Group has this other standard that they developed over the last several years called the Device Identifier Composition Engine, or DICE for short. And the model behind DICE doesn't have a separate isolated environment in the TPM that holds measurements. Instead, what it does is it says, why don't we hash the next layer for its measurement? But what we're going to do is we're going to pass a secret up to each layer of software during the boot process. The secret is going to start out initially with a unique device secret, and there's going to be this engine that always performs this function after power on. What that engine is going to do is it's going to measure the next layer. In this diagram, that's layer 0. And it's going to combine that measurement with the unique device secret, and that's going to generate a secret. If you boot the same layer 0 code, you're going to get the same secret when you combine the measurement of layer 0 with the unique device secret. We use a one-way function, so there's no way to reverse engineer what the unique device secret is in layer 0. And we'll pass that secret 0 up to the next layer. So layer 0 starts out with its own secret, and then the process repeats. Layer 0 can take the hash of layer 1, and it can combine that with a one-way function with secret 0 and produce a secret 1 and pass secret 1 to layer 1. Layer 1 can do the same thing with the successive layers. This is a way to have a secret for each layer that's really representative of the device identity, as well as the software that's booted to load that layer and the layers before it. This is really a different model from the TPM. So, this requires that somehow the hardware actually has this device identifier composition engine that starts the process. It has this persistent unique device secret that it's able to access, but is not accessible to any of the software later. So the DICE engine takes the unique device secret, measures layer 0, combines those in a one-way function to generate secret 0, passes secret 0 to layer 0. And that kind of process repeats itself. There is special support needed in the hardware to be able to make the unique device secret not accessible to later layers. But layer 0 doesn't need that type of special support for secret 0, because secret 0 is just in memory. And it's a transient value that it could just zero out memory before it transitions control and passes secret 1 to layer 1. How this gets used is if you have an update of software, maybe you know that there's a problem in layer 1, a vulnerability is discovered for it. What you do is you deploy layer 1 prime on the platform. Then what's going to happen is everything through the boot process stays the same to compute secret 0 because layer 0 stayed the same. But when layer 0 goes to compute the secret, it's going to pass to the next layer. The hash of layer 1 prime is different. Its measurement's different. So when it combines that with a one-way function with secret 0, it produces secret 1 prime instead of secret 1. And it passes secret 1 prime to layer 1 prime. And then the similar activities happen to continue the boot process. So each layer actually holds a secret that's representative of that unique device secret and the software at its layer and below it. This can be used to show to another entity that this device has, booted specific software and what the device identity is. This is a very similar thing that we could do with a trusted platform module with the measurements that are stored as integrity measurements in the TPM and the quote that's used to sign those measurements. Kind of looking at how this could be implemented in practice, this is a diagram of DICE implementation that Microsoft has open sourced. You have this bottom layer that's the SoC that has a DICE engine and it has access to that unique device secret. It computes something called the compound device identifier, which is the secret for layer 0. And it passes that up to what hopefully is a very stable core implementation of just a very thin layer to help set up this architecture. The compound device identifier can be used to generate a very long-lived device identity that doesn't change if the DICE core layer of software doesn't change. The DICE core gets measured by the DICE engine to get combined with the unique device secret and produce that compound device identifier. So what you have is a way to have a very long-lived device identity. And then the process can continue for the next layer up by generating an alias key that is kind of secret 1. It has the firmware security descriptor of the next layer of firmware combined with the compound device identifier to make that secret for layer 1. You can also generate certificate chains as you go up through the layers if you're using asymmetric crypto for an implementation. And the device identity can be long-lived, and there's a way to show at each layer of software to some third party or a cloud management server what software is booted and what the device identity is. So this is a really low-cost implementation of the same objective we had to do with the TPM around device identity and what software is running on a platform. It's really useful for IoT not to have that extra cost. So then the question is, we've looked at some examples of IoT security and how they could be done in ways that are less expensive. The question is, how can we bring that to market? And really the recommendation for the industry is development needs to continue to happen around these other security techniques for IoT that are lower cost and lower resource intensive. So IoT manufacturers will start to pick them up and put them into their solutions. And really what we have an objective of is to have remote management for IoT devices. We know we need this ongoing support for devices during their deployed life cycle. Ideally, that's done by a cloud-based management of the device so it can happen at scale. We need a device identity. We kind of talked about 2 different ways to be able to make that happen with DICE or with the TPM. And then you need this ability to do measurement and attestation based on roots of trust. So you can really trust that it's not malware giving you misinformation about the device state. And then earlier we talked about the resilience engine that gets invoked reliably as the platform is started. It doesn't need a separate isolated environment to do its stuff. It could use the main IoT processor because it's running in that early boot environment where the manufacturer has, or the IoT solution developer has complete control. Ideally though, it's hard to ask every IoT solution developer to go do this themselves. Instead, what needs to happen is IoT platform manufacturers need to incorporate roots of trust and security into their tool chains and their initial software they provide to help initialize devices, and provide ways for IoT solution developers to use those features that are very simple and easy. IoT solution developers really should be able to focus on their functionality. The other thing that could help with this too is trying to have security infrastructures. Everyone that's doing specific functionality shouldn't have to build a mechanism to deploy updates. Ideally, an infrastructure exists that's able to make things simple for IoT solution developers to be able to focus on their functionality. What this type of model looks like is you, instead of having the solution developer that's working on their specific functionality do everything around provisioning, patching, management, they just focus on their specific functionality and the online services associated with that application. And there is this larger infrastructure that's provided by some entity that's able to do this for a variety of different solution providers. The solution providers can just focus on their functionality, but the infrastructure to do roots of trust, to do attestation, to be able to manage device identity is all provided as a service from some other entity that's able to help support the product through their life cycle, able to focus on those security considerations that many IoT solution developers aren't aware of or aren't experts in. It's like creating a sandbox environment for application-specific functionality where the solution developer can just focus on that. And this is a great trend for the industry to go towards, and something that I'd advocate trying to get to. Instead of having to have everybody reinvent the wheel around how to do security infrastructure, try to get these things standardized so functionality can be in a sandbox, and outside of that sandbox, all the other security infrastructure can be done by a provider. And that's the end of what I wanted to cover. I'm happy to answer any questions if people have any at this time.
A couple questions here. You talked about security efforts from the Trusted Computing Group of Microsoft. Are there any industry efforts to improve IoT security?
I would say there are a ton of industry efforts. I mean, I only had time to talk about a couple today. So, I think everybody wants to solve this problem. Everyone has this concern about IoT and what's going to happen when too many devices are deployed and then they're attacked by malware. So, this is just my attempt to give you one slice of the piece I'm working in. I'm going to show some references for where you could find more resources on this. But there are definitely other efforts within the industry too.
Awesome. And then another one here. You provide recommendations for the industry to help improve IoT security. What are Microsoft's efforts to follow that advice?
I think Microsoft has been evolving its IoT security capabilities along with the rest of the industry. We're working towards providing something that we're calling Azure Sphere, where we would help somebody be able to focus on just their functionality piece, and we would do a lot of the security infrastructure for a lifetime of a device. But we also have, cloud services where people can build their own device and send in telemetry for analytics and business insights with just the Azure IoT Hub. For that, we've got a bunch of SDKs that help you do device identity based on a TPM, based on DICE, based on a hardware security module or a certificate, or if you really wanted to, you could also do your device identity based on software protection of it. I think we're doing some more work to try to bring capabilities around attestation. It's simpler to do attestation and understand what should be on an IoT device than it is for a PC platform, just because the amount of software on an IoT device is a lot simpler and less complex. So I think we're making improvements there. We also have like Windows IoT, which is an OS for IoT devices. I think the thing you get from that that's a benefit is it has that infrastructure to deploy updates, just like the regular version of Windows does. At the same time, it does require a lot more resources for an IoT platform. So those are just some examples. You know, we're involved with the Trusted Commuting Group. We've got a cyber resilient platforms program that we've got information posted on from Microsoft Research. You know, we're trying to be engaged with the industry and help work to solve these problems. I think at a high level, though, we really think the bar should be set pretty high for what IoT security is. I think it's a matter of trying to race to bring all those components and organize them in a way and get them delivered so they get adopted in IoT solutions in the marketplace.
All right. Thank you so much, Rob, again for hosting, and thanks everyone for attending. This will end the webinar for today. Thank you so much. Bye.
Thank you.